Pharmacy and Management IFDP-HCAMPM 2026, we continue our journey of gaining insightful knowledge and exploring the transformative role of human-centric approaches in modern industries. Today, our expert lecture promises to enrich us with valuable perspective of Industry 5.0 and operational excellence. It is now my proud privilege to honor and introduce and welcome our distinguished expert speaker for today, Dr. Santosh Rane, who is currently serving as the head of the Department of Mechanical Engineering at Sardar Patel College of Engineering, Mumbai. Dr. Santosh Rane is highly accomplished academician, researcher, and industry expert with more than 25 years of extensive experience in quality improvement, business excellence, and industrial problem solving across diverse sectors. He holds prestigious MTech and PhD degree from VJTI Mumbai and is certified as Master Black Belt in Lean Six Sigma from Indian Statistical Institute. He is also CII certified supply chain management executive and completed advanced training in project management from SPJIMR Mumbai. Dr. Rane has made remarkable contribution to research and innovation with more than 120 research publications, over 3,000 Google Scholar citation and H-index of 25 and 26 patent, out of which 12 have been granted. He successfully guided 13 PhD scholars and has played a vital role as a corporate trainer and consultant for globally reputed organizations such as TUVSUT and Bureau Veritas. His expertise has benefited thousands of professionals through more than 450 business excellence and training projects. He is also a recipient of several national awards and holds key leadership role in professional bodies. Today, he will be delivering his expert talk on the topic Industry 5.0 Human Centric Practice to Improve Employee Engagement, Safety, and Operational Excellence. This topic is highly relevant in today's evolving industry landscape, where integrating human value with advancement technology is essential for sustainable growth and organization success. On behalf of Shriram College of Engineering and Management and all the participants, I extend a heartfelt welcome to you, sir. We are truly honored to have you with us for today and eagerly look forward to gaining valuable insight from the vast knowledge and experience. I request Dr. Santosh Rane, sir, to kindly take over the session.
Thank you, madam. Shall I share my slide now?
Yes, sir.
Whether my presentation is visible?
Yes, sir.
Fine. Whether my voice is loud and clear?
Yes, sir, it is.
Yes, sir.
Thank you. First of all, I give my sincere thanks to my guru, Professor Premanand Chauhan sir, for giving me an opportunity to get associated with you all through this international FDP on application of human-centric AI in manufacturing, pharmacy, and management, organized by Shriram College of Engineering and Management in association with Institution of Engineers India, Gwalior Local Chapter. Today's topic is one of the interesting topic of this FDP, that is Industry 5.0 enabled human-centric practices to improve employee engagement, safety, and operational excellence. I congratulate Chauhan sir and his entire team for organizing this important FDP for the benefit of the mankind and all of us. So let us start our discussion with the basics. What is the difference between Industry 4.0 and Industry 5.0? These things that might have been already discussed in the earlier session. So I shall quickly go through these things just as a revision. So let us take the dimension foundational philosophy. In Industry 4.0 enabled manufacturing, it is technology-driven digital transformation, whereas Industry 5.0 enabled manufacturing, it is human-centric, sustainable, and resilient transformation. So there are three important characteristics: human centricity, second, sustainable, and the third, resilience. And there is a shift from automation-centric to value-centric manufacturing. Then we move towards the primary objective. The primary objective for Industry 4.0 enabled manufacturing is efficiency, productivity, and the automation. Whereas in Industry 5.0, the objective is balanced productivity with human well-being and the sustainability. As a strategic implication, we say it's a broader performance evaluation beyond the operational key performance indicators. Now, with reference to the role of human workforce in Industry 4.0 enabled manufacturing, it is supervisor of automated systems and there is a reduced manual role. In Industry 5.0 enabled manufacturing, there is an active collaborator role with intelligent systems and augmentation focus. So there is a enhanced skill utilization and cognitive engagement. Then human-machine relationship in Industry 4.0 is automation and system control, whereas in Industry 5.0 enabled manufacturing, it is human-AI cobot synergy and co-creation, where collaborative intelligence ecosystem is a strategic implication. With reference to the technology, IoT, CPS, big data, cloud, AI-driven automation are the typical technologies used in Industry 4.0. Along with these technologies in Industry 5.0, cobot, human AI interfaces, and ethical AI adaptive systems are also used. So here in strategic implications are evolution from smart to collaborative systems. Now, with reference to the workplace design in 4.0, those are digitally connected smart factories, smart organizations, smart systems. Here in Industry 5.0, these workplaces are ergonomic, safe, shared human-robot workspace where the robot and the operators both work at a time at the workstation. They augment each other's capabilities. So there is an integration of ergonomics into system design. With reference to the safety, in Industry 4.0, there is an isolation-based safety. So fencing and the separations, where the robots are working in separate zone and the supervisor is watching and controlling or monitoring all the robotic operations from the extended control. Then in Industry 5.0 enabled manufacturing, it is intrinsic safety, where force limiting, proximity sensing, shared space. These are the specific characteristics, and strategic implications are engineering controls embedded in system architecture. With reference to the manufacturing model, Industry 4.0 emphasizes mass customization through automation, whereas Industry 5.0 emphasizes on personalized manufacturing through human-machine collaboration with increased responsiveness to complex customer needs. With reference to the decision-making structure, 4.0 emphasizes on data-driven algorithm optimization, whereas 5.0 emphasizes on human-in-loop intelligent decision systems with major emphasis on ethical and contextualized decision-making. With reference to the performance metrics, Industry 4.0 focuses on overall equipment effectiveness, throughput, downtime, defect rates, and many more. Whereas in Industry 5.0, we move beyond these performance metrics along with engagement index, ergonomic score, sustainability index, resilience metrics with expanded KPI architecture, including social indicators. So here you can see there are many dimensions which we can discuss, like sustainability focus, innovation paradigm, workforce skills required, organizational structure, economic orientations, and many more. I will move forward. I shall be sharing this slide with you all. So with reference to Industry 5.0, I have taken a case study of Industry 5.0 enabled manufacturing so that all the essential characteristics of 5.0 can be appropriately correlated in the manufacturing case study and can be studied in a better fashion. So let us look at this. Industry 5.0 pillar and their applications to the ceiling fan manufacturing company. Here, the pillars like human centricity. The core principle is technology augmented human capabilities. In ceiling fan manufacturing applications, those are collaborative assembly workstations, operator decision support, and ergonomic design. The second pillar is the sustainability. So core principle is environmental responsibility and the circularity of the supply chain. The ceiling fan manufacturing application emphasizes on energy efficient productions, waste reductions, and the product life cycle optimizations. The third important characteristic of 5.0, that is the third pillar, is resilience, and the core principle is adaptability to disruptive forces. So here we'll be having the production lines with better flexibilities, cross-trained workforce, and the supply chain visibility, transparency, and the traceabilities. Now, to have better involvement, I tried to involve you all in the multiple choice questions so that there will be more attention. In the transition from Industry 4.0 to 5.0, what is the evolving role of humans in ceiling fan assembly line? So there are the four different options: operating only manual tools, monitoring industrial robots in cages, creative problem solving and product customization, eliminating automation roles, automations completely. So the answer is creative problem solving and product customization. Next. When we talk about the 5.0 enabled manufacturing, and digital twinning of this system, there are the 5 different layers. With reference to the timeline, I would try to curtail the discussions on the digital twinning part. However, I will touch some of the specific elements of these things. There are the 5 important layers in the digital twinning of the system. The first layer is a physical layer, where we will be emphasizing on human-cobot collaboration. The essence of the modern manufacturing is human worker and the cobot working in close proximity. So the cobot is actively assisting the assembly of the ceiling fan, where the heavy workpieces are lifted by the cobot and the repetitive jobs are done by the cobot, whereas the operator has the responsibility of carrying out some destructive activities and taking some smart decisions, logical decisions. Another MCQ for us: the flexible production lines and cross-trained workforce contribute mainly to which Industry 5.0 pillar? So there are 4 options available: sustainability, human centricity, and the resilience. And the last is automation. So flexible production line and the cross-trained workforce, these are the essential requirement to address the disruptions in the systems. And based on that, we say that resilience is the correct answer. Next to that, there are the key characteristics of human-cobot collaborations and manufacturing. These characteristics are available as shared workspace with the specialization as human-cobot operate without rigid safety cages. So they work in tandem, they augment each other's capability, and there is a sensor-enabled proximity monitoring. Second, complementary skill integration, where human dexterity and the robot precision, they complement each other. Then cognitive flexibility and mechanical repeatability, they complement each other to perform the task and create the better performance. Then with reference to the task allocation and the optimization, cobots handle repetitive activities, repetitive jobs. Cobot handle heavy material and the precision-based tasks, whereas the human manage the complex assembly, inspection, decision-making, some dexterous activities. Then right time interaction and the feedback, like visual, tactile, sensor-based communication get established. Then there is an adaptive motion control. Whereas with reference to the ergonomic enhancement, there is a reduction in the manual lifting and strain, whereas improved workplace posture and the comfort. Now, with reference to the flexible and modular manufacturing, there is a quick adoption to different fan models based on the customer requirements, and there are the easy reprogramming and redeployment for manufacturing of these different fan models. Now, with reference to the human-centric design philosophy, worker remains central to the system, where we say that it is a human centricity and the technology augment rather than replacing the human being. So built-in safety intelligence in the system, like force limiting sensors, collision detection sensors, speed monitoring sensors are installed in the system at the appropriate places, so that the robot and the human being, they work together in a very safe workplace. Then reduced physical barriers like open layout production, sales, and the improved accessibility to the work, to the ongoing work. So the barriers are removed or reduced. That increases the accessibility. And next to that, the continuous learning capability like data-driven process improvements and the AI-assisted optimization. Now, the human-centric manufacturing framework has the 4 different levels like foundational connectivity, augmented capabilities, collaborative systems, and the human system integration. With reference to these things, there is another multiple choice question available for us. The stage where technology enhances the worker's skills and the performance is referred to as where technology is enhancing the worker skill. So we say that there is a augmented capability. So that is the level 2. Now there are the key characteristics of the human-cobot collaborations. What we have already talked about, like shared workspace, then complementary skill integration, then task allocation, optimization, ergonomic enhancement, uh, uh, enhancement, including the reduction in manual lifting and strain, then reduced physical barriers, flexible and modular manufacturing, human-centric design philosophy, and so on. Now, the another MCQ in the context of Industry 5.0, what is the primary characteristic that differentiates human-cobot collaboration from traditional industrial automation? So we have the options: cobot completely replace the human labor. Second, human primarily supervise cobots. Third, cobot work alongside human in shared workspace, augmenting human capability. And the last option, cobot are designed for tasks that are too complex or dangerous for humans to perform alone with minimum human input. So in Industry 5.0, cobot and humans, they work with each other. And that's why the answer is C. We move ahead in Industry 5.0 enabled manufacturing. So performance parameters influenced due to Industry 5.0, these are listed as productivity parameters, quality parameters, safety and ergonomic parameters, human performance parameters, operational excellence parameters, financial and strategic parameters. If I think about the productivity parameters, then cycle time reduction, throughput rate, overall equipment effectiveness, line balancing efficiencies, idle time reduction, and changeover time. These are some of the sample parameters what I have listed over here. There are many more parameters. Next, with reference to the quality, few sample parameters are listed over here, like defect rate reduction, first pass yield, then the rework and scrap reduction, assembly accuracy, consistency of fastening the torque, then process capability in dissects like CPCPK. So process capability index, critical process capability index. Then with reference to the safety and ergonomic parameters, lost time injury frequency rate, then musculoskeletal disorder incidents, near miss incidents, safety compliance index, worker fatigue index, such kind of parameters are available, and there are multiple parameters. However, I have listed sample over here. Then with reference to the human performance parameters, employee engagement level, skill utilization ratio, job satisfaction index, learning curve improvement, cognitive load reduction. Then operational excellence parameters like process stability, downtime reduction, MTBF, MTTR, resource utilization efficiency. These are some of the operational excellence parameters which are going to be influenced heavily due to Industry 5.0 enable manufacturing. Now, if we see from the finance and strategy point of view, then cost per unit, then return on investment, labor productivity, energy efficiency, asset utilization percentage, then flexibility index for the mass customization. These are some of the parameters which are influenced because of Industry 5.0 enablement. So those things are given over here, like productivity parameters, quality parameters, operational excellence parameters, human performance, and the financial. Now we continue our journey with reference to the Industry 5.0 enabled fan manufacturing, where ergonomic and safe places are further discussed. Now, 5.0 ensures comfortable work posture. The work surface is at an appropriate height. Appropriate illumination is established. Robot design is smooth, lacks the sharp edges. The presence of protective eyewear on the worker. The use of the appropriate PPE kit if at all necessary. Then organized nature of tools and components suggest the clutter-free and the safe work area. So to continue the discussions with reference to 5.0 enabled ergonomic and safe workplace, the first is human-centric ergonomic design with a major emphasis on optimized workstation height. So work surface aligned with the anthropometric data. Anthropometric data means body dimensions. That promotes the neutral spine posture and minimizes the bending and overreaching. This reduces the strain. Then posture supporting layout. This encourages the proper body mechanics, by virtue of which the appropriate efforts are being utilized to the fullest extent with minimum strain, reduces the musculoskeletal strain, supports the long duration task comfort. Now, visual ergonomics and illumination. Uniform and adequate lighting like bright, shadow-free illumination, enhanced precision assembly with reduced eye fatigue. So these are some of the characteristics of 5.0 enabled visual ergonomics and illumination. Then improved visibility, like better defect reduction, reduced inspection errors, and lower cognitive loads. Then we continue our discussions. The intrinsic cobot safety design emphasizes on smooth structural geometry with rounded edges, no sharp protrusions, reduced physical injury risk in the workstation design. Then another important dimension is the force limiting sensors. Here, the control, torque, and speed sensors are available. Then these are used at the appropriate locations. Automatic stop during collisions, safety human-robot proximity, safe human-robot proximity. All these are the typical characteristics based on the force limiting sensors. Then adaptive motion control and real-time interaction safety are the typical characteristics of speed and proximity monitoring as a part of the 5.0. Then, with reference to the use of protective eyewear, compliance with the safety standards, prevention of eye injuries, reinforcement of safety culture, these are the essential dimensions which are captured as a part of use of protective eyewear. Now, visible safety protocol adherence, like standard personal protective equipment usage, behavioral safety enforcement, these are some of the essential dimensions which are captured with reference to the visible safety protocol adherence as a part of the Industry 5.0. Then structural tool arrangement, like logical placement of the tools, reduce search time, then improved workflow efficiency, by virtue of which all the unnecessary stress and strain and chaos, those are eliminated. Then lean and 5S based layout, where 5S is established with reference to the 5 important steps of like sorting, setting order, shine, standardizing, and sustaining. Then reduced trip hazards, faster material access, and so on. Now, with reference to the clean and well-maintained environment, there are the points like housekeeping excellence and the preventive maintenance culture. So housekeeping excellence that is established through dust-free and orderly surroundings and reduced contamination risk. Then the equipment reliability and lower accident probability, these are the important dimensions with reference to the preventive maintenance culture. Safety integrated shared workspace, that particular characteristic will take care of no rigid cages, intelligent safety systems, engineering controls over administrative control, and proactive hazard prevention. Worker well-being and sustainability orientation will emphasize on ergonomic optimization, lowering the physical stress, clean, organized, and well-lit environment, improving the morale, then technology supporting the human comfort and worker dignity and safety are prioritized. So the another MCQ for us, in the context of Industry 5.0, which of the following best describe the primary focus of ergonomics and safety in human-robot collaboration environments? Here we have the 4 different options, A, B, C, D. Designing the systems where human and robots safely and efficiently coexist and interact, prioritizing the human well-being and cognitive load. Then maximizing robot autonomy and minimizing human intervention. Third, focusing solely on reducing physical strain. And fourth, implementing extensive physical barriers and strict separation zone between human and robot. So as per the 5.0 characteristic, we say that the first option is correct. Designing system where human and robot work together. Then in fan manufacturing, we need the various equipments like CNC machines, injection molding, press machine, winding machines, assembly machines, and the balancing machine. And their typical primary applications are also shown over here, along with the Industry 5.0 enhanced opportunity. So if I take an example of CNC machine, here the Industry 5.0 enhanced opportunity is digital twin simulation, predictive tool wear monitoring, operator guidance systems. Then in injection molding, real-time process optimization, quality prediction, energy management. Then pressing machine, here ergonomic material handling, quick change tooling with augmented reality guidance, condition monitoring. Then in winding machine, there is adaptive tension control, operator decision support, predictive maintenance. In assembly machines, there is a collaborative robotics, vision guided operations, adaptive workflows like this. Then we have the another MCQ, ergonomic material handling and augmented reality guided quick change tooling are primarily related in 2. So here there are the 4 different options, CNC machines, winding machines, pressing machines, and the assembly machines. So with reference to the fan manufacturing, these are the 4 different machines listed out. And here we would like to identify where these ergonomic material handling and augmented reality guided quick change tooling are related. So the answer is pressing machine. So all the sheet metal working machines, they need this with the major emphasis. Now let us move towards the employee engagement metrics and the improvement targets. So what are the typical metrics like frontline employee engagement, intent to stay, that is continuity of the job, then employee net promoter score, skill training access, recognition effectiveness, and the internal promotion rate. So here you can see the current typical baselines are given. And in Industry 5.0, the targeted improvement that is also shown over here with the improvement factor. Fine. Now with reference to the technology, safe technology applications by manufacturing zone, you can see there are the various machines available in the various manufacturing zone. And there are the typical hazards and there are the 5.0 enabled safety solutions. So for example, in stamping division of the blades, there are the moving machineries, heavy loads, and the noises. So in Industry 5.0 enabled system, there is a proximity detection, machine guarding with the AI monitoring, noise exposure tracking, and so on. So such kind of systems are established. In motor winding, there is a repetitive motion, pinch points, whereas in Industry 5.0 enabled system, there is a ergonomic analysis, footing monitoring, automated lockout and tagout. In assembly shop, there is a repetitive strain lifting. So here you can see in Industry 5.0, collaborative robots, which give the assistance for the lifting, then posture monitoring, adaptive workstations. In testing, there are the automated test sequence, remote monitoring, energy isolation verification. So in this manner, we can refer the safety technology applications. Now, operational excellence, key performance indicators, and the Industry 5.0 contributions. Under the key performance indicator categories, there are the indices like with reference to the productivity, quality, equipment effectiveness, energy efficiency, material yield, worker contribution, and safety. Their typical traditional metrics are available, like for productivity is units per labor hour. In Industry 5.0 enhancement, it is the human-machine collaboration efficiency and the improvement we can expect up to 25%. Now, with reference to the quality, the traditional metric is a defect rate. In Industry 5.0 enabled manufacturing, it is AI predicted quality prevention, quality enhancement through defect prevention. So as good as 50% reduction further. Then equipment effectiveness, that the traditional metric is overall equipment effectiveness. So here we are using the predictive maintenance, digital twin optimization. So there is a 20% improvement in OEE. With reference to the energy efficiency, AI optimized consumption, where 30% reduction in the energy utilization based on the AI optimized consumption. Then material yield, there is a reduction in the scrap. So process optimization and predictive quality. So 40% reduction in the scrap is expected. Worker contribution, that increases up to double. So innovation enablement platforms, that is the specific characteristics of 5.0 enablement. And with reference to the safety, here the near miss or accidents reduction up to 70%. So these are some of the advantages with reference to the typical parameters. Now here we have the another MCQ. The introduction of innovation enablement platform doubles the employee suggestions per year. So which KPI category demonstrate this Industry 5.0? We have the 4 different options: productivity, worker contribution, quality, equipment effectiveness. So worker contribution is a typical category demonstrating the 5.0 shift. Fine. Then we move towards the training and change management requirements. So here we have the various stakeholders as the audience, like executives, plant managers, supervisors, operators, technicians. So almost all the different um, uh, roles are captured over here, and they need the typical training. So executive needs the training with reference to the human-centric strategy formulation, technical overview, and the cultural change. So what kind of method is being used over there? The workshops, executive sessions, timeline, it is always ongoing. Then plant managers, the major focus of the training is implementation of the leadership, change management approach, and formulation of the metrics. So delivery method is intensive workshops, pre-phase 1 timeline. Supervisors. The major focus for supervisor is coaching, communications, along with the new tools for evaluating the performance. Then delivery method is blended learning. Timeline is pre-phase number 2. Then operators, who are the frontline operators carrying out the necessary work. So digital tools, collaborations, problem-solving tools, delivery methods are on-job training, micro-learning, and timeline phase 2 onwards. Technicians, technology implementation, maintenance, technical training, phase 1, 2. All implies vision, benefit, expectation, town hall kind of a delivery method. Those are used and those should be ongoing. So let us move towards the MCQ. The company wants to ensure the top level cultural transformation before implementing Industry 5.0 technologies. Which training intervention should be prioritized? It is workshops and executive session for the executives. Fine. Another, if the objective is to improve the operator problem solving skills using collaborative digital tools, the most appropriate delivery method would be, there are 4 different options: executive strategy session, town hall or corporate communications, on-job micro learning, and intensive leadership workshops. As here, these are the operators. So naturally, executive strategy sessions, not possible. Intensive leadership workshop, that is also not applicable. Only 2 are remaining, town hall and on-job. So town hall is for the masses. Here we are specific to the operator. So we will use the case C, that is on-job micro learning. And that is the correct answer. Next, when introducing new digital tools and collaborative systems, supervisors should primarily undergo. There are 4 different options: blending learning focused on coaching and communications, only executive strategy briefing, purely technical coding sessions, town hall awareness session. Here, these are the supervisors. So naturally, we can say supervisors are supervising the workers. So here we need the blended learning focused on coaching and communication. So answer is A. Next. Now we move toward the risk assessment and the mitigation strategies. Now risk assessment with reference to the technology, workforce, operational, and regulatory. In technology, specific risk, cyber security breach. The likelihood is medium, impact very high. So mitigation strategies should be defense in depth, regular audits, and incident response. And we should have the appropriate digital culture in place. Then another, integration technology, integration failure. So likelihood is medium, impact is also medium. Whereas the mitigation strategy is phased integration, testing, vendor support, consistent vendor support. Now, with reference to the workforce, there is a possibility of the worker resistance to adopt the Industry 5.0 enablement. Likelihood is medium, impact will be very high. So we need to get them involved in Industry 5.0 enablement. We need to communicate the benefits of Industry 5.0 to the workers. And we have to develop the peer champions in the worker themselves. Fine. Then another, with reference to the workforce, privacy concerns. So likelihood is very high, impact is medium. So mitigation strategies are privacy by design. We will design our system foolproof to ensure the privacy and data localization and the transparency. Next to that, operational risk. So the specific risk is implementation disruptions. So when Industry 5.0 is enabled, there is a possibility of disrupting the existing system. That is always possible. So there is a medium likelihood of the same, and the impact is also medium. So we will go in phase 1, phase 2, phase 3, step by step. So, and there is a pilot testing before actually implementing it. And then we must have the contingency plan to address this particular risk and so on. So then we have the another MCQ. A company plans phase digital transformation but faces moderate workforce resistance with high impact potential. What strategic approach is most effective? So there are the four different options: immediate full-scale deployment, technology-driven enforcement, early employee engagement, and outsourcing implementation. So the answer is early employee engagement. Next to that, the power exoskeletons and the collision avoidance systems are particularly relevant to which of the following manufacturing zone. So maintenance, material handling, stamping, forming, motor winding, these are the four different options available. And in material handling, we need to handle the heavy loads. And for that purpose, the powered exoskeletons, these are useful to us. Okay. Now we move towards the another important dimension, that is a sensor rich environment as a part of the digital twin enabled Industry 5.0 enabled fan manufacturing system. So here the sensors are appropriately identified for capturing the almost all different technical parameters of the system. These sensors are fitted in typical XYZ orientation to capture the various parameters. And these sensors are capturing the live data and sending it to the cloud through IoT gateway and the edge computing. So this is a sensor-rich environment. So here we say the Copod utilize the advanced sensors to understand their surrounding fan manufacturing workstation. These sensors allow them to accurately perceive fan components. This perception is crucial for precise manipulation during the fan assembly. Then working closely with humans, Copod employ sensors for collision detection. So these prevent accidents and ensure the safe shared workspace. The sensor enable real-time avoidance of the obstacles. So beyond safety, the system uses sensors for monitoring the assembly process. This monitoring is vital for maintaining the quality control. So another MCQ, in an Industry 5.0 sensor-rich environment, what is the key benefit of integrating the diverse sensor data like environmental, then physiological, machine performance for human workers? There are the four different options available. It primarily automates all decision-making processes, reducing human cognitive load to minimum. Next, it facilitates proactive interventions for worker safety and well-being, optimizing the human cobot collaborations, and provides personalized training and support. Its main purpose is to reduce the operational cost, and the last, it enables the creation of digital twin of the worker. So based on the discussions, we can select the correct option as B. It facilitates proactive intervention for worker safety and well-being, optimizing the human-robot collaboration. Fine. Then to continue our discussions with reference to the human involvement, humans are in loop. So there is a direct physical interaction between the cobot and the human. Humans are actively working on the assembly floor, directly handling the fan motors, blades, control units as they move through the line. There is a cognitive skill integration where workers apply their unique problem solving and adaptability to complex steps like balancing the fan blades or diagnosing subtle operational issues. Then the task demanding high dexterity, such as connecting dedicated wiring within the fan motor casing or securing intricate control board components, these are performed by humans. Then in the real-time problem solving, operators physically troubleshoot and resolve unexpected issues like a misaligned fan housing or a faulty sensor during assembly. Then human perform crucial tactile and visual inspection, ensuring the blade alignment, smooth rotation, and aesthetic finishes of the ceiling fan. Workers can quickly reconfigure workstations or adapt to variation in fan sizes, styles, or smart features on demand. Human actively use and adjust specialized tools and fixtures for tasks like attaching blade arms or securing the components. So these are the typical characteristics when human are in loop. Let us move ahead with the respective question. In Industry 5.0, the concept of human in loop primarily signifies a system. So there are four options: a system where human workers are constantly monitored by AI, the active and continuous involvement of human intelligence and decision making in complex tasks. Third option, complete automation of all production processes. And the fourth option, human being responsible for all manual assembly tasks. So as per the definition, we say that the active and continuous involvement of human intelligence and decision making in complex tasks. That is the concept of human in loop. Fine. The second important layer of the digital twinning of the manufacturing system is the development of the virtual layer. It has its own typical quality characteristics. I shall be discussing few of them because of that time availability. So here, our objective is to establish the virtual twin, virtual replica of the physical asset. So when I say digital twin, there are the two important entities. One is a physical asset and another is a digital replica. The digital replica has all those typical features what the physical asset has. Okay. So when we are installing the sensors on the physical asset, we must install the sensors in the digital replica also. Okay. Now, 3D digital model and AR VR interfaces, augmented reality and virtual reality. There is a simple difference between the augmented reality and virtual reality. So when we say virtual reality, it means the physical object is somewhere else. It is not in front of the operator. Operator is only visualizing the virtual reality. That is the virtual image of that physical object. That physical object is not in front of the operator. When I say augmented reality, in that case, the physical object is available in front of the operator, and operator is using the digital tools for understanding the intricacy and the complex architecture of the physical asset. That is the augmented reality. Now let us move ahead with this 3D digital models and AR VR interface. So comprehensive digital twin of the products. So 3D digital model create highly accurate virtual replicas of the fan component from motor housing and blades to intricate wiring and control boards. So virtual prototype design iteration. Before any physical metal is cut, engineers use these 3D models to rapidly design, modify, test numerous fan configurations, optimizing aesthetics, aerodynamics, structural integrity virtually. Then performance simulation and analysis. These models allow for sophisticated simulation of ceiling fan performance such as airflow patterns, noise levels, energy consumptions, structural stress under various conditions long before the physical production begins. Fine. So another MCQ for our discussions. What is the fundamental difference between the augmented reality and the virtual reality? I have already discussed those things, so I shall directly move ahead with this. So augmented reality enhances the real world view with the digital content, whereas the virtual reality create a fully simulated immersive environment. In virtual reality, the physical object is not available in front of the operator. In augmented reality, the physical model, the physical asset is available in front of the operator. Fine. Then the 3D models, augmented reality, virtual reality interfaces. So remote expert assistance via AR, VR. Experts can remotely view the factory floor in AR, VR, guiding on-site technicians through complex repairs or quality checks on a ceiling fan by annotating the live physical view or demonstrating actions virtually. Collaborative design and review. Stakeholders from different departments or global locations can collectively review and make real-time adjustment to 3D fan designs in shared virtual spaces and accelerating the product development cycles. Then in predictive maintenance and digital monitoring, 3D digital twins of actual production machines like robotic arm assembly fans can be linked to real-time sensor data allowing for virtual monitoring, predictive maintenance, and simulation of potential failure before they can occur. With reference to the quality control and inspection, augmented tools can be used to compare the physical ceiling fan against its perfect 3D digital twin, highlighting any deviations or defect immediately, thereby streamlining the quality assurance process. So here we have the another MCQ. Beyond simple failure prediction, what advanced capability does the sophisticated digital twin enable for predictive maintenance? There are the 4 different options: automatic negotiation with suppliers, then real-time remote control of physical asset from operation from anywhere, then remaining useful life estimation, automated creation of spare part manufacturing orders. So with reference to these things, we can say that remaining useful life estimation and prescriptive maintenance recommendation, that is the best capability developed based on the digital twin enabled systems. Now we move towards the next activity, that is the what if analysis as a part of the second layer, that is virtual layer. So there are the various scenarios and we carry out the simulation for, let us say, the simulation for design changes. Design changes with reference to the blade, motor housing, and new features. So what if we change the angle or material of the fan? So instead of using the metal, if we use the FRP, then what will be the impact on the cost? What will be the impact on the supply chain? What will be the impact on the environment? So the virtual layer can simulate airflow, noise output, energy consumption, structural integrity to predict performance without molding a single physical blade. Now, with reference to the motor housing, what if we use the lighter alloy for motor housing? Simulation can assess its thermal dissipation, vibration, durability under various operating conditions. So new features, what if we integrate smart home connectivity or new lighting features? Then what if analysis with reference to the manufacturing process optimization? Now, if I take an example of a production layout, what if we reconfigure the assembly line, perhaps moving the motor winding station closer to the final assembly? The virtual model can simulate new material flows, robotic path, human-cobot interactions, and overall cycle time to identify the most efficient layout. Another automation level. What if we introduce the new cobot for blade attachment or packaging? So simulations can assess its impact on throughput, labor requirements, and potential bottlenecks. The resource allocation. What if we reduce the number of human operators on a specific shift? Virtual model can predict the impact on production capacity and the quality along with the cost. Then what if analysis for the supply chain and material variation? So material substitution. What if the specific plastic for a fan canopy becomes unavailable and we need to use the alternative material? So virtual model can test the new material fit, finish, durability, impact on assembly processes, and the entire life cycle cost. Then the component delays. What if the critical component like ceiling fans remote control module faces a supply delay? So simulation can model the impact on the production schedule and inventory levels. Then scenario simulation with reference to the quality control and the failure analysis. Defect propagation. What if a minor defect occurs at an early stage, like slight imbalance in the motor? The virtual model can predict how this might propagate. Then sustainability simulations, core principle. So here, unlike traditional methods, Industry 5.0 virtual layer allows manufacturers to proactively design for sustainability. Instead of reacting to the environmental impact, they can predict and mitigate them during the design and planning phase. So digital twins as the foundation, highly accurate digital twins of every component, the entire assembled fan, and even the manufacturing processes themselves are used. These virtual replicas serve as the testing ground for sustainability analysis. Then energy consumption analysis, product use phase. Simulations can precisely model the operational energy consumption of different ceiling fan designs. For instance, varying blade angles, motor types, control systems can be simulated to predict energy efficiency rating over the fan's life cycle. This helps select design that minimize the user electricity bill and the carbon footprint. So the virtual layer can simulate the energy required to produce the different fan components or assemble the fan. We have the another MCQ in hand. What is the primary goal of using proactive sustainability simulations during the design phase of a new manufacturing process? So there are the four options: to train the new employees on how to operate existing machinery, to identify and fix environmental issues, to predict and optimize the resource consumption and waste generation before physical implementation, and to determine the market demand for the product being manufactured. So the answer is to predict and optimize the resource consumption before physical implementation. Fine. Then the sustainability simulations like waste generation analysis, the material utilization. Simulation track the material usage efficiency for various fan designs and production methods. It can predict the amount of scrap generated during processes like injection molding for fan casing or cutting fan blades from raw sheets. End of the life scenarios, the virtual model can assess the recyclability and the disposability of the components. For example, it can analyze how easily a fan's motor can be separated into its constituent metal for recycling, or if different plastic types in housing hinder effective recycling. Then environmental impact assessment, like raw material extraction, manufacturing, transportation, use phase. So these cover all these typical entities. Then sustainability simulation, product variations for a sustainability focus. So recyclable blades, motors. A manufacturer can simulate the use of, say, recycled PET plastics for blades. The simulation would compare not just the cost and performance, but also the embodied energy, reduced landfill waste, lower carbon emission associated with the recycled material. Similarly, for motors, assessing the feasibility and environmental benefits of using easily recyclable core materials. Then modular design. Simulation can evaluate how a fan designed with easily separable components, snap-on blades, easily detachable motor assemblies would impact future repairs, upgrading, recycling processes, enhancing its longevity and sustainability. Modular design will help us to assemble the components easily with minimum time, minimum efforts, and minimum cost. Then informed decision making. The insights derived from these simulations empower engineers and designers to make data-driven decisions that balance performance, cost, environmental impact. They can virtually compare different material choices, manufacturing processes, and design features to identify the most sustainable options without costly physical trials. Then we have that another important layer that is called as a data layer, where data from the machine in ceiling fan manufacturing processes, so in ceiling fan manufacturing plant, machines perform various critical operations. Real-time data from these machines is essential for monitoring the performance, predictive maintenance, quality control, and optimizing the production. So what kind of data points are essential? Winding speed in RPM, electrical parameters like then number of turns, coil resistance, motor temperatures, vibration controls, vibration levels, machine uptime, downtime, error codes, power consumptions, power factors, many more things. There are the insights like detect anomalies in winding quality, predict motor winding failures, optimizing winding parameters for energy efficiencies, track production progress, and many more. The data layer, the data points can be mold temperature, injection pressure for plastic blades, stamping force for metal blades, cycle time per part, material usage, number of defects, uneven finish, deformities, then machine startup, running, idle time, fault identification. So insights are ensure consistent blade quality, identifying the root cause of the defect, optimize cycle time, monitor machine health. Then assembly lines. The data points can be robotic arm position, velocity, torque applied during screw fastening, component pick and place accuracy, and many more. In the next 2 minutes, I would like to just go through these things. So the fourth layer is the analytic layer where the explainable AI is used, which give the justification for the action. Then in analytic layer, the personalized decision support systems are available for the maintenance technicians. The resilience modeling is done. The last layer of the digital twin is the application layer with reference to the actual application. So role in 5.0 where human experience is enriched with intuitive, inclusive, and responsive applications. So role-specific dashboards are available, like operator, supervisor, executives receive customized interface showing relevant key performance indicators, alerts, and the suggestions. So voice-controlled and AR assistant systems are available. Co-creation portals are available. Fine. All these are the part of the Industry 5.0 enabled manufacturing. The last layer is a business layer. With reference to the business layer, there are the different KPIs. Okay. And then this continues. The case study redefining the fan manufacturing that is sourced from this typical research article. Okay, so this is the full-length discussion. I would like to conclude the exploration of the Industry 5.0 in the context of fan manufacturing industry illuminates a transformative pathway towards sustainable development and enhanced operational efficiency. This study's focus on digital twin technology with Industry 5.0 underscores its potential for revolutionizing the manufacturing processes, fostering socio-environmental sustainability. Industry 5.0 presents a paradigm shift from profit-centric model of Industry 4.0 towards more human-centric approach, emphasizing the prioritization of the human needs, socio-environmental responsibilities, and increased resilience. The integration of the digital twin into manufacturing process serve as a pivotal enabler for intelligent machining production lines, holding immense promise for the industry future. So digital twin will redefine the user experience and play a significant role in increasing the efficiency and effectiveness of the products, processes, systems, organizations, supply chain, value chain, and the nation. It established a remarkable blessings to the mankind. Thanks to all of you. So with this, I conclude my session. Hello.
Thank you so much, sir, for such a wonderful and enlightening session. With great enthusiasm, let's begin the questioning part. So, those who have any question, any query can raise their virtual hand and ask to sir.
I shall be sharing this presentation to sir, and I request sir to kindly share with you all. This covers many things. I skipped many slides. It's a full-length presentation. So it will help you to move ahead with this basic Industry 5.0 enabled case study in fan manufacturing company.
Thank you, Raniji. Very nice presentation. If you permit, may I ask something that is general segments? Because you have shared the case studies related with the fan industry. Do you have data on how many industries have implemented Industry 5.0 concept? Especially we'll talk about the India and the world. Are we doing work on it? Any researchers or this data available here?
Sir, industry have started the journey, but the real implementation will take time. In many industries, they have already established Industry 4.0 enablement. Now they are moving ahead with Industry 5.0, where the worker and the cobot both will work together. So that activity they have started. However, they have to reach to the maturity level. For example, in there is a factory, automotive company that established the complete Industry 4.0 enabled manufacturing in Chakan.
Okay.
So they are moving ahead with 5.0. So the efforts have been already started. However, the maturity will take a little time. We
Yeah,
will see
definitely.
these things in the 1 or 2 years,
Yeah.
because people need some training to work with the cobot.
Means it is in the evolving
Yeah.
paradigm. And next is, how do you see the future evolution of Industry 5.0 in the Indian manufacturing concept over the next decade? Because in the foreign countries, especially USA, Canada, France, Germany, it can be implemented easily, very easily. But if we talk about the Indian context, still we are talking about the automatic lathe machine, automatic milling machine. We are not 100% implemented the CNC machines, especially the IoT with the CNC. So what is your view on it?
Sir, we have huge variety as such. There are the micro level industries, then small scale industries, medium scale industries, and the large scale industries. At micro level industries, we cannot expect these kind of systems available. Even small scale industries, we cannot have these kind of systems available. So for establishing these kind of systems, we need the investment. And the another part is finally the return on investment. Small scale micro industries, small scale industries, most of the times they are the vendors to the big industries. As they are the vendors to the big industries, they depend on the orders what do they get from the big industries. So they don't want to invest the capital in these kind of technologies. Now the large industries, they have the capitals and they also have the system, particularly possibility to implement these systems. So they can take these kind of decisions for adopting these technologies in their premises, depending on the return on investment. So for the particular product which has already reached to the maturity level and having a very good kind of a demand, for that kind of a product, they can go for adopting these technologies.
Nice, you nice. Any other participant? If you have any query, you may ask. Before concluding the session, there is an important announcement. In the next month, we are planning to organize a workshop on importance of publication and patents and how to publish in good and top rated journals. Especially we talk about the top rated journals. How do you check the quality of the journals? How can we define the Q1, Q2, Q3, and Q4 journals? At the same time, what is site score? What is the role of the impact factors? We will definitely discuss on all these parameters. And Professor Rane will be the one of the key person there. So we were discussing on that point before starting the session. Thank you, all the participants. Now over to the host. Yes, Pallavi ma'am.
Thank you.
So before concluding, I guess Madhvi ma'am wants to ask something because she's continuously raising her hand.
Yes, yes, yes. Please, 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 please. Okay, just a minute.
The significance of KPI, sir. KPI.
That is key performance indicator.
Okay, sir.
Thank you, sir.
Yes,
I have a
Madhvi.
quick question, Dr. Arane.
Yes, madam.
How much does, I know you come from academia, how much does your organization collaborates with industry in terms of engaging your students? with the industry.
Miss, you want some information with reference to my organization, or you're talking with reference to our main session?
Yeah, your organization. You are the head. Yeah.
So this is something different than my today's session. Am I right?
Correct. But I mean, it's a very good topic. But I'm just wondering, because you are covering this topic for the in the academic setting, for these educators who want to incorporate Industry 5.0 into their teaching. So any industry learning comes from learners' engagement into the industry. And that's why I'm asking that question.
So what is the question? Will you please repeat?
Yeah. So how much does your organization, your educational institution, incorporates with industry for student learning?
Madam, we have the MOU with various organizations, and we have the professional organizations student chapter. For example, we have the student chapters like Society of Automotive Engineers, and we conduct multiple workshops, training programs, certification programs under this banner, where the people from the industries like vice presidents, general managers, senior general managers, CEOs, they come and they give the necessary orientations, training to the students. Some specific keynote speeches are also organized. Then some conclaves are being organized where there is a industry academia interactions. Then our alumni who are placed in the different countries, in the different organizations and securing the top positions, they are also invited as alumni speak program. And that is a regular activity. And they help our students with reference to giving the overall idea with reference to their job profile, then the necessary skill sets for their job profile, what are the perspective ahead, what are the different opportunities and the challenges ahead in that particular domain. It may be the oil and gas sector, it may be the banking sector, or it may be the data analytics kind of a job. So what are the roles, responsibilities, the specific challenges, opportunities available? So they interact with the student and they give the necessary orientation to the students. And that is a regular practice. For example, we have also established the Blue Star Center of Excellence. So Blue Star experts, they come to institution and they regularly conduct the hands-on training workshops on the state-of-art laboratory established in the domain of HVAC, heating, ventilation, air conditioning systems, refrigeration systems by Blue Star. So the hands-on training is given by these experts to our students, and students, based on that, they get developed their skill sets. So that is a regular practice. Then we also had the MOU with Siemens. So for their typical software like a product lifecycle management, the specific course has been designed, and that course is embedded in our curriculum. So in this manner, the Siemens experts, they come to institution and they give the specific training to our students, and the student get the benefit in terms of knowledge, skill sets, and finally leading to the best placements. So, and all these are the common trends what we are following. Yeah. I hope
Wonderful.
this
Thank
answers
you.
your question.
Yes. Wonderful. Thank you so much.
Thank you, madam. You are from which institution, madam?
Oh, I'm not in industry. I'm just a curious person.
Okay. You are from industry. Okay, fine. Thank you.
Thank you so much, sir, for patiently answering all the questions. We deeply appreciate your time, guidance, and contribution to this faculty development program. With this coming to an end of the session, wishing everyone a productive and enriching journey ahead. Tomorrow again we will connect at the same time with Mr. Prafulla Chandra Bose. Till then, thank you everyone. Stay connected, stay inspired. Have a wonderful evening.
Pallavi madam, can we have the screenshot of photograph of
Sure,
all?
sir.
So
Sure,
if
sir.
everyone switch on the camera, then it will be a very good kind of a screenshot.
Sure, sir.
Yeah, definitely.
So
You
please
kindly,
announce accordingly.
kindly remove
All the
sharing of the screen. Kindly remove sharing of the screen.
All the participants are humbly requested to please turn on their cameras so that we can have a perfect screenshot for today's session.
The still slide is on. Yes, yes.
Pallavi madam, you can take the screenshot.
Sure, sir, but your screen is still shared onto my screen.
Okay,
Yeah.
okay, fine. Then I shall stop sharing.
Yes, sir.
Now you can take. Done?
Sir, just 2 minutes.
Yes, done, Ranaji.
Okay. Thank you. Thanks to all
Thank you
of
so
you.
much, sir.
Once again, thanks to all the audience for attending the session. Once again, thanks to my guru, Chauhan sir, and Pallavi
Thank
madam
you.
for all the
Thank,
necessary cooperation. Thanks
thank
to
you,
the
sir.
entire
Very
team.
interesting session. Thank you. Thank you very much.
Thanks to each one of you.
Thank you, sir.
Bye-bye. Bye-bye. Bye-bye.
Bye.